Now, we can talk about why things attract or repel based upon electricity, but you're in luck. We're not only going to talk about why things attract and repel because of forces. We will come up with 3 other ways to explain the exact same thing. I know, exciting. We'll have 4 explanations for the same phenomenon. I am assuming that you have watched the video, so I'm trying not to repeat too much of that. All right, so if I have a positive charge here and I have a negative charge there, what's going to happen to them? Okay, why? Yeah. All right, so in terms of forces, opposites attract. So explanation number 1. Opposite charges are attracted to each other. The forces are attracted to pull towards each other. Let's go to the next one. No, this was one of the videos. If I have a positive charge here, I have a universe with just a positive charge in it, and I put a negative charge into that universe. What's going to happen between these 2 charges? Yeah, it's the same problem as that. So the big question is, how does the positive charge know the negative charge exists, and vice versa? To be attracted, they must know that they exist.
I think one of the videos said we don't really know, but it's like maybe he said a pheromone.
Electric pheromone, yeah, and again, I'm the only person who's gonna call it that, but they had to come up with a better name than that. Although there is a couple of terminology. Plasma is a terminology that started as a biology term and then leaked over to a physics term. Prion is a biology term and a physics term, but they mean 2 completely different things. I'm assuming that was just, they were picking up concrete or something. So what is the official name for these electric pheromones? It's interesting that you picked that part out, but not the official name. Sorry, spoiler there. The electric field. Now, of course, we have to have a symbol for electric field because I don't feel like writing that out the entire time, so we got to come up with something special for it. And so we tapped into our creative spark there and just used E with the vector symbol. It is a vector. Please do not confuse the magnitude of the electric field with energy. Energy. Magnitude of the electric field. Because one way of representing the magnitude is just to drop the vector symbol, but because of that confusion there, I will try to do the magnitude like that instead of just not writing the vector symbol. Am I 100% on that? No, but I try to be. All right, so electric field, first off, has to exist with only one charge. Because when the negative, I can't stick a negative charge in there and suddenly it goes, ooh, I guess I better turn my electric field on. It has to exist already for the negative charge to know that positive charge exists. And as soon as the negative charge gets thrown in there, it creates its own electric field, which the positive charge will sense with its spidey sense. Now the formula, well, I know that the force, some constant, times charge 1 times charge 2 over R squared. This would be the electric force on 1 from 2. Again, E for electric. So the electric force. Force is getting worse and worse there. Electric force on Q1 from Q2. So if Q1 and Q2 are opposite charges, so one's positive, one's negative, I'm going to get a negative value here, and it'll be in the negative R2 hat direction. And R hat, which I think we first formally dealt with when we dealt with centripetal motion, R hat is a unit vector, thus the hat, pointing away from some central point. And so if it's negative, that means it's the direction of the force is towards it instead of away from it. So if Q1 and Q2 are both positive or both negative, this whole thing is positive, and so the force on 1 will be away from 2. That's the math part of it, which no doubt thrills all of you to the core. Now, electric field exists except without that, I have only one charge there, so my electric field formula can't have 2 charges in it. So they cleverly just removed the charge. So the electric field from 2 would be K, this Coulomb's constant, times Q2 over R2. So it looks a whole lot like that, it's just we just removed one of the charges. So if Q is positive, so let's say I've got some charge 2 right here. If Q2 is positive, what is the direction of the electric field at this point right here? Because K is positive, R squared is going to be positive. So if Q is positive, this whole thing is positive. What is the direction of the electric field? So I got a finger pointing this way, and a finger pointing that way. I will tell you, it is one of those 2 answers. Can we please get a tiebreaker? Oh, there we go, we got a tiebreaker. We now have 2 fingers pointing in that direction, just one pointing in this direction. Where do you place the money? Was that a random point, or you just decided to sort of speak up?
Sort of both.
Okay. Your gut says we're not 100% confident?
Yeah.
You are correct. It is indeed pointing in that direction. Now, obviously we need to review this special unit vector there. R hat, a unit vector. Pointing, because it is a vector, it's got to have a direction, pointing away from the center. Now, what is the center? It depends upon the problem. In this case right here, I have just a single charge here. The center would be the center of the charge. So 3 meters R hat is a vector that's 3 meters long, pointing away from the center. So if my center is right there, this vector would be a vector pointing away from it, and it's 3 meters long. That also would describe that vector and that vector and that vector, and just, there are times when it's advantageous to have this, and other times when using I hat, J hat, where you got right angles in there. Negative 3 meters R hat, and that's my center right there, would be a vector pointing towards it. Now, it's not just those four directions, it's pointing towards it no matter where you are in there. I just got tired of writing after 4. So, if everything here is positive, then my electric field is in the positive R2 hat direction, which means it's pointing away from Q2. So over here, it's pointing that way, up here, it's pointing that way, there, it's pointing this way, there, it's pointing that way. Yes?
If anything in that equation is negative, does that make it to where it automatically points to?
Yes.
Okay.
The only thing in there that can be negative is the charge. So the electric field points away from positive, and it points towards negative. So as soon as that universe is created and we stick a positive charge into it, it immediately starts giving off these electric field lines, which I refer to, as was mentioned earlier, as electric pheromones. So we have this electric field. I guess I should keep it within the universe. This electric field sort of going out. So the negative charge doesn't know a positive charge is there. All it knows is there's this electric fields. So let's talk about that part. If I have an electric field going to the right, there are 3 possibilities. I can have an electric field going to the right if I have a positive charge over on the left-hand side. I could have a negative charge over here. Or I could have both, positive there and a negative there. Those are the 3 things that would create an electric field going in that direction. Into this, I throw a negative charge. If I throw the negative charge here, what is it going to do? I got a positive charge here, negative charge here. Getting various hand gestures, people afraid to speak.
Go towards each other.
Towards each other or away from each other? They're opposite signs. So you're sticking with it, go towards each other? Did you want to change your mind?
Well, here they're.
I'm looking at just this situation right here. They're opposite charges. What do we know about opposite charges? Yes. So this will be pulled in that direction. If I throw a negative charge into this scenario, what's it going to do?
It'll stop before it gets to the other one.
Well, we just stick it in there at rest. Ashley, your point, okay, we got a thumb pointing that way. Why?
Because, oh wait, no, yeah, because they're the same, so they want to,
Yeah, they repel. It's going to go that way. And in this situation down here, if I throw a negative charge, which way will it be forced? Yeah. Got more than 3 fingers very quickly. I think you were pointing, yeah. Because it's being attracted to this and repelled by that. So in every single case, it is going against the flow. I will sometimes refer to it as it'll go upstream. So I can now throw into the problem. I have an electric field going to the right. What's causing it? Don't know. Doesn't matter. I put a negative charge into that electric field. Which way will that electric field go? If I put a positive charge into that electric field, ignore that. Which way will the positive charge go? Liv, what was that gesture? Okay. Anyone want to back her up on this? All right, somebody's got your back. Got 3, up to 3 now. Can we get a 4? 4 people with the same answer? Somebody might have done a subtle gesture and I just missed it. like to think that all of you have done it, I linked it the wrong way. Which way will the positive charge go? Is that a gesture there, Ashley?
Maybe.
Be brave, be bold.
Wait, ignoring the negative charge?
Yeah, ignoring that. All I know is there's an electric field going like this, throw a positive charge into it. And KB, correct. Yep, all right, we've got five people who all agree that the positive charge is gonna go that way. We can generalize this. A negative charge in an electric field is forced the opposite direction of the electric field. And again, the three scenarios from the other screen, negative charge doesn't know anything other than there's an electric field going this way, I want to see what's that way. Whereas positive charges go with the flow, the electric field's going this way, positive charge goes, hey, I wonder where it's going. And then a positive charge in an electric field is forced the same direction of the electric field. As of one of those words. All right, questions to hear before I put two pieces together and come up with our second explanation for why an electron would be attracted to a proton or repelled by another electron. Caroline, you had the look of, I'm not sure I can read his handwriting.
This is opposite direction, right?
Yeah, opposite direction, I got lazy, just stopped at DIR. All right, let's put the two pieces together. A positive charge creates an electric field away from itself. A negative charge creates an electric field towards itself. Toward or towards. Again, toward is American and towards is British. Is it something like that? A negative charge. Oh, and then I'm just going to rewrite what I had over there. So if I have a positive charge, if I had a positive charge and a negative charge, and I wanted to explain why the negative charge comes towards the positive charge in terms of the electric field, it is a lot wordier than opposites attract. But there's a reason why they do this. The positive charge will create an electric field away from itself. The negative charge will sense that electric field and go in the opposite direction, which means it's towards the proton. And that is the explanation for why an electron would be attracted to a proton. If I switched it around and I said, which way will the proton be forced? Well, it's going to go towards the electron because the electron produces an electric field towards itself. The proton's going to sense that and go in that same direction and head towards it. Two explanations for the exact same thing. Got forces and electric field. Any questions before we add a third one on? I can feel the anticipation. Yeah, we're about to do it. Woo! Now, right now, we've dealt with two vector stuff. Surely there's gotta be a way of doing this without vectors. There it is. Let's just talk about energy for the moment. I have a particle here at rest. If it is at rest, what is its kinetic energy? I saw somebody with the hand gesture, actually two hand gestures, just to emphasize it. Let's go ahead with that. Why is it 0?
It's at rest.
Pardon?
It's at rest.
Okay, let me ask the question. Let's bring that one back. Prepare yourself. It's gonna sound like the Chorus of Angels, I know it will. What's the formula for kinetic energy? Not quite the chorus I was hoping for, but. So if V is 0, K is 0. If it starts to move, what's happening to the kinetic energy? Look for something simple. Increase, decrease, stay the same. Okay, so if it goes from rest to something to not rest, kinetic energy goes up. If it is doing that because of a conservative force, what's happening to the potential energy?
Is it decreasing?
Yeah. Because the total energy stays the same, so if kinetic energy goes up, potential energy has to drop. So if kinetic energy increases under a conservative force, then the potential energy must decrease, and vice versa. So if we could look at this in terms of energy, we can look at it that way, that